Well, good evening, everybody. Thank you for coming and being part of the Haverhill Science Festival, set up and run by the One Haverhill Partnership in conjunction with the Town Council and other partners. This is a wonderful thing for the town, and there's been lots of activities, particularly engagement with schools, designed to get people thinking about science and STEM and getting different aspects of the community involved in lots going on around the town. And we're looking forward to Saturday with lots of community activities, including the space where you're sitting being transformed into a planetarium. And if you go online, you can book tours of the planetarium, which will take you through different aspects of the solar system as you walk through that. But tonight, this year's focus in terms of STEM is mathematics, and it is a great pleasure to be able to welcome the Reverend Dr. Alex Shannon, Vicar of the Pant Valley Churches, Finchingfield, Weathersfield and Great Bardfield, plenty of other parishes in that direction. Alex is a good friend of mine. We trained together at Westcott House and we're on many of the same courses together, so we've shared much of our journey of formation and training together at least, and are now back within striking distance of each other, although we don't see each other quite as often as perhaps we should. Alex's PhD is in mathematics, and he's then read further study, higher study in theology. So he is aptly placed to speak to us this evening on mathematics and spirituality. His talk is entitled The Maker of Patterns. And we very much look forward to hearing, Alex, what you have to say. So welcome, and thank you for being with us tonight.
Thank you very much, Max, for the invitation. It's a great pleasure to come and talk about a subject that's very dear to me. I was thinking earlier on today, when putting the finishing touches to tonight's talk, about my own journey of faith, which has led me to ordained ministry in the church. And there are a number of strands in it. Obviously, my own church involvement growing up, but that went very much hand in hand with two areas of passion for me, which continue to be the things that most interest me. One is the world of science and mathematics, the other is music. All areas where patterns are of fundamental importance for being able to kind of build things, to appreciate beauty, and to see how those things link together. I was very fortunate, actually, to be in a school where our science department worked very closely with the religious studies department to discuss these sorts of questions about science and theology. And I think it's so important that we do address them in a modern world where science and religious belief often come up for debate against one another. It's important for us to also see how they nourish one another and support one another. And I hope that point of view will be evident in what I have to say this evening. So the title of the talk I have borrowed from a great Cambridge mathematician, good to be in the right vicinity there, G.H. Hardy, one of the foremost mathematicians that this country has ever produced. From the early 20th century, a great contributor to number theory and parts of analysis that feed into that. And he is perhaps also widely known around the sort of fringes, perhaps, of the mathematics community for a very important book that he wrote called A Mathematician's Apology, which was essentially his manifesto setting out why he thought it was important to study pure mathematics, mathematics for its own sake, independent of particular applications to the natural sciences. And he wrote in that book, a mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it is because they are made with ideas. One of the things that perhaps we are taught to think when we think about mathematics in opposition or contrast perhaps to other areas of the sciences, particularly if you hear a mathematician talking, it has to be said, is that they will tell you that mathematics is all about proving things that are absolutely, utterly and eternally true, perhaps even pronouncing it in such a way as you might think it has a capital T. This is one of the ways in which mathematicians start to veer into what might even look a little bit like theology. Because they will quite happily tell you that they are absolutely 100% certain that certain mathematical statements are true, not just because they have done the arithmetic and tested out that particular formula for one number that you might put into them, but because they have a logical argument that says this will hold for absolutely any numbers that you put into this formula, this theorem, whatever it might happen to be. Whereas they will say the patterns that scientists deal with, natural scientists deal with, are always subject potentially to being overturned by the next experiment uncovering some new phenomenon which forces everyone to go back to the drawing board and come up with a new theory to supersede the old one. However, we also know, and mathematicians like myself will have to admit in our moments of kind of more humility, that indeed there is a very great connection between the kinds of patterns that we observe in the logic-filled world of mathematics and the much messier and more complicated world that we live in and observe and try to understand through our scientific endeavours. And indeed, over the course of this talk, we are going to be looking at a number of examples where the patterns that we see around us flow naturally in their description from the very bare minimum, perhaps, of assumptions that we might make about the physical processes underlying those phenomena, then infused with the arguments of mathematics to say, well, actually, if we make those very small number of very reasonable and justified assumptions, then we know, logically speaking, that we will have to observe something a bit like this. And my question really for this evening, the central question that I want to think about, is where do those kinds of patterns come from? Because we might suppose that patterns in the world around us come about because somehow the universe has been set in motion in some very neat, well-designed way so that those patterns arise. The patterns that come from the setting up the way in which the universe is so that that beauty and pattern emerges, then maybe we also need to think that God lies deeper, even in the very realms of how we think and how we reason about the world around us. So that's sort of where we're likely to go. But I want to start by thinking about the ways in which we imagine God acts as a kind of creator of things. And I want to start with a point of view that I'm going to kind of dismiss quite quickly. I think it's important to start with it, not least because it is a point of view which has started to grow in prominence, not only amongst certain groups of Christians that we might term as more fundamentalist, but also because it's become, if you like, the version of Christianity against which those who are opposed to the idea of science and religion being in harmony with one another, against which they are have a tendency sometimes to argue. So this first view of creation, if you like, is one where, I don't know if there are any Douglas Adams fans in the audience. Anyone? I've avid reader or viewer or listener of the Hitchhiker's Guide to the Galaxy series. So for those of you who are familiar with that set of books will know about the great beings of Magrathea, the ones who in Douglas Adams' universe make custom-built planets, and the Earth in that series being an example of their handiwork. And this is actually most clearly set or made visible in the most recent film version of The Hitchhiker's Guide to the Galaxy, where you actually see the planet designers working on what turns out to be a replacement Earth. I hope I'm not giving away too many spoilers for anyone who was intending to read the books but hadn't done so. And you see people, painting the spots on animals and things like that, setting up little blades of grass and flowers in exactly the right position, all ready for someone to light kind of blue touch paper, at which point everything starts to burst into life and something goes go. So we might imagine certain artistic representations of creation where we see, as it were, God moulding the universe and then simply saying go, and everything is already set up, all the different creatures being as they are. So, this is a point of view which has never really been held seriously by Christian theologians, even in the very earliest stages of the church, because actually, in the earliest days of the Christian church, we had already had a few centuries passed since the great thought of the schools of Greek philosophy, who had thought very carefully about the principles of creation and where creation might come from. And indeed, we have the likes of Plato and Aristotle to thank for many of the philosophical insights on which more sophisticated views of what God would be like to take. So perhaps a slight refinement of the view that I've just given is to say that the universe and its relation to God as creator is more like the relation of a composer to a symphony, that somehow everything has been notated in a great deal and then it's handed over to the performers to make what they will with. But that's still not quite as firm a commitment as perhaps we would like to make to the idea that the scientific laws that we observe in the world around us have a great deal of integrity. We might think that a commitment to the idea that the universe, according to scientific principles, is something that comes from the scientific revolution, perhaps from the era of Galileo onwards, strengthened further in the Enlightenment as the scientific method began to crystallise. But actually we can go a couple of centuries earlier than that and find ourselves well inside the Christian tradition. And we have St. Thomas Aquinas writing in the 13th century, commenting on Aristotle's work of physics. And in describing what creation looks like, he says this: "It is as if the shipbuilder were able to give to the timbers that by which they would move themselves to take the form of a ship." This has a number of advantages, both from a traditional and a modern standpoint, for us thinking about God's relationship to the patterns in the world around us. Firstly, it preserves the integrity of the scientific success that we have seen around us, the way in which we have been able to understand a universe which, as Einstein said, its greatest mystery perhaps is that it is in some sense comprehensible. The other thing, of course, though, is the idea that we should be committed to a universe where things evolve according to predictable patterns is an important theological idea. The reason it's an important theological idea is that if the universe were to evolve simply from moment to moment on the whim of some external being, then any sense we might have that we had freedom to act as agents and individuals within the universe would be completely compromised. what use is it being able to control your actions if you have no idea about how to tell what will happen as an immediate consequence of those actions? So, in fact, the idea that the universe obeys set laws that God does not readily break, in some sense, is one which is important for us in our philosophical view, if we hold that we, as creatures, have some meaningful kind of free will. So, this is the sort of picture we have of creation that has been set forward many times now, and there have been many really wonderful apologists for the harmony of science and theology, particularly over the last half century or so. And again, to think back on my own journey of faith, one of the great moments I look back on was when one of the visiting speakers who came to talk to our group of schools in Canterbury, where I grew up, was none other than Professor Sir John Polkinghorne, who lately, of course, also of University of Cambridge, great theoretical physicist who was then ordained as a priest and wrote many books and articles identifying the sort of harmony that he found existing between natural laws and those patterns and his Christian faith. As I alluded to, though, in the introduction, I think that actually perhaps one of the things that we need to think about is whether the relationship between God and creation goes even one degree deeper, and that the very language that we use to talk about the world around us, the language which has proved so successful in formulating all those scientific theories that we perhaps might be thinking about, the language of mathematics has something of God's mark in it too. So with that in mind, we're going to move now to think about some particular examples of how, in the world of mathematics, the sorts of intricate, complicated and beautiful patterns we observe in the natural world come to arise. And we're going to start, again, there's a bit of a theme of some Cambridge connections here with the mathematicians being talked about. John Horton Conway was for a while at the University of Cambridge and contributed to a mind-boggling array of different areas of mathematics. He seemed to flicked between different areas that appeared at first glance to have nothing to do with one another and find deep and surprising connections between them. But one of the things that he's perhaps best known and loved for in his writings and discoveries, the way in which he tackled various mathematical games. And he came up with one particular idea for perhaps a game in a slightly stretched sense of the word, in that this is simply, if you like, a little computer experiment. And one which attracted the interest of many people in the early days, particularly of computing, when it first began to become accessible to hobbyists rather than people who needed access to the machines that filled whole rooms. And this was an illustration, one of the earliest illustrations perhaps, of a rule, a very simple to explain rule, producing patterns that can be very and really completely surprisingly complicated. He called this the game of life because he thought that this might have a toy model, if you like, for seeing how lifelike structures could originate from very simple principles. And the idea is that you have a grid of squares, and each square in your grid, as you might think of the blue square coloured there, is surrounded by 8 other squares that are touching it, either sharing a side or a corner. And each square in this grid is either left blank or it's coloured in. And we sort of interpret this in the rules of the game as a square being either dead or alive. Alive if it's coloured in, dead if it's not. And so for each square, surrounded by its 8 other squares, at each step in time, we have a rule to decide whether or not it goes from being dead to being alive, from alive to being dead, or stays in its current state. So if the square that we're starting with is alive, then it survives if 2 or 3 of the surrounding squares are alive. Otherwise, it dies. The idea being that life, in order to survive, needs other life around it in order to help sustain it. But there's too much other competitor life surrounding it, then it causes it to snuff out. So this was derived as a kind of balance to say that overpopulation and underpopulation lead to the death of life in a particular area, otherwise it gets sustained. But similarly, then you have a reproductive principle, which is to say that if you have a dead square, a blank square, and it's surrounded by exactly 3 alive squares, then it comes to life. So you can have a look at what this looks like. So this is a starting pattern. In order to play this game, you need a starting seed, if you like. And this pattern, if you can't see the individual squares, then you can take it on trust from me that there are 8 in. 3 all in a line, then a gap, and then 4 arranged in a square with 1 sticking out underneath. And amongst people who study the game of life, this shape, this particular seed shape, is known as an acorn, because it gives rise to a most extraordinarily intricate pattern. And I'm going to play the video and you can see what happens, just using the rules that we looked at on the previous slide. So you can see, to start with, it sort of goes about, stays, and then as time goes on, you see little islands begin to emerge that sort of stay in a well-behaved way. You can see that 4 squares, all in a square shape, those sort of blobs stay stable. You see that there's another one that's emerged just at the top of the pattern, 0, that also is stable. There's now a few examples of 3 in a row that alternate between being vertical and horizontal. And then actually now at the bottom of the screen you can see one that's sort of flashing in between something that looks like an incomplete circle and an incomplete cross shape. So we're sort of letting this carry on, seeing how it evolves. And it looks like it's sort of staying more or less roughly contained, very similar sort of behaviour. It doesn't look like it's going to do anything very different until we just let it run a little bit longer. And as we let it run a bit longer, we see it is gradually expanding outwards. We've got more of those stable islands appearing. And if you look now towards both the top and the bottom of the screen, you will see some little arrangements of 5 cells which are making a bid for freedom. So I now zoomed out and recentered the image so you can see what's going on. And indeed, those 2, they're called gliders by people who study this. They're now making their bids for freedom, escaping from the world, moving off in that way, whilst various other processes happen behind them. And so it continues. At some point, relatively soon, the speed at which each step there speeds up so that we can see what happens in the longer term. You can see some more of these what are called gliders zooming off. You might even, if you look carefully, spot one that collides with another blob and they disappear, or it changes its shape or something like that. And so off we go. There's another one making a bid for freedom, but still plenty of activity going on in the middle of the picture. But a lot of those stable patterns, the sort of winking ones, the stable ovals and blobs being there. And we're just going to let it run one little bit further, because you might at this stage be thinking, well, this is just going to go on forever. It's going to keep expanding, getting more and more complicated, and we will it'll just sort of get bigger and bigger and bigger, more and more complicated. There'll be lots more going on, and it could go on like that forever. So let's say I'm just moving the field of view so you can see a few more bits of stable pattern that have appeared. And the surprising thing that we get to is that actually this is after between 5,000 and 6,000 steps of the game, so you've been quite through a lot of it. We've got a position where now obviously those gliders that we saw disappearing off, they're still going off to infinity, and nothing will stop them now. But everything else that's left is just stable. The video is now stopped, but those patterns that were winking before, oscillating between two different states, will keep going. And when people started to experiment with this, they thought, well, this is just extraordinary, that this really simple set of rules that you could just write down in a very small number of sentences can, with actually not a very complicated starting pattern, produce something like this. Another example that we're going to turn to now about how things that perhaps look even more like real life in the natural world can arise from simple mathematical patterns comes from the world of fractals. Fractals were one of the great achievements of mathematicians, not only because they have some beautiful and very intricate mathematics behind them, but because they make wonderful pictures. And so they are, if you like, the absolute PR hit for mathematics from the 20th century. And particularly when you can see that they replicate in just such an extraordinary way natural forms. Now, the reason that this picture of a fern has these slightly odd colours and rectangles round it is to explain why this is such a simple pattern to describe. Because if you look at the black rectangle that surrounds the sort of picture as a whole, and imagine that that was made out of rods that could be lengthened and shortened, held together at the corners in such a way that the corner angles could change freely, then you could imagine sort of shearing, rotating and expanding and contracting that rectangle in such a way as to form the three four-sided shapes that you see in light blue, dark blue and red, the rectangles surrounding those parts of the fern picture. And actually, it's very important for the mathematics of this to work out that you also need the stem. So there is also a sort of green line that you can see, which comes from squishing the rectangle this way so that one of its lengths is 0. Now, this picture is the unique picture, as in the picture of the fern, is the unique picture which stays the same if we make 4 copies of it and squish, stretch and shear them in the same way that we squish, stretch and shear that black rectangle to make the 3 rectangles and the sort of not quite a rectangle but a line that comes from squishing it all together completely. So all you need in order to describe this fern mathematically is the coordinates of the corners of the 4 shapes that big rectangle is transformed into, or some other similar way of encoding it. In other words, need it amounts to 6 numbers for each transformation, so that's 4 transformations, 24 numbers. 24 numbers to encode that extraordinarily lifelike picture of a fern. And just perhaps even the principle of the geometry of how you turn those numbers into the picture, even that is not terribly complicated. So both of these two examples that we've had a look at have something really important to tell us about what it is that we imagine that we're seeing when we think about patterns arising in mathematics and in nature. In both cases, the thing that sort of made them stand out was that we were able to describe something which looked complicated, intricate, even lifelike, with a very small amount of information. And there is a word, a concept, which we can use to try and make that idea precise. And the word in question is entropy. Now, entropy has a long and very, very interesting history. It originated in the study of thermodynamics, in the study of how efficient you could make a steam engine, or how you could transfer heat from one body to another. And indeed, the best known exposition of the concept of entropy comes from the great comic song duo of Michael Flanders and Donald Swann. If any of you have heard their take on the first and second laws of thermodynamics, then you will know a little bit of what I'm about to be talking about. If you haven't come across that one, I suggest you seek it out, because it is the most wonderful, accurate, and also hilarious presentation of physics in song that you could possibly imagine. Entropy is a way of describing, on the one hand, we think of it as a measure of disorder, or chaos, randomness. On the other hand, we also think of it as a measure of information. Now, these two things seem perhaps to be a little bit opposed to one another. If something contains lots of information, surely that means that it's not disordered, it's got lots of structure in it. But the way in which those two concepts relate to one another is that if something is highly patterned, like the fern or the game of life pattern that we saw previously, then even if it looks intricate and complicated, we can actually describe it using a very small amount of information. So those structures, those patterns, have what we would term a low entropy. Whereas, if those structures that we were looking at didn't arise from some underlying pattern that we could use to generate that picture or that form, then we would have to specify, if you like, each individual little bit of that picture individually. So that would take a lot of information, rather than just being able to run a relatively simple computer program to tell us the answer. The other thing, if you've met the concept of entropy before, that you are likely to know about it, is that it always increases with time. That is the famous, perhaps in some circles even infamous, second law of thermodynamics. And this has been popularised in sort of scientific popular culture, particularly because if you apply it to the whole universe, one of the things it seems to as the universe evolves, all of the kind of structure and things that underlie the way that the world is made up will dissolve, and all that we'll be left with at the end is some kind of uniform soup of matter that doesn't have any structure in it left at all. To see what this law of physics looks like, what it means, we can look at one particular example. It's a relatively simple example. We're imagining that we've got two gases, and the gases are made up of molecules that are moving around inside a box, and they're different colours, so that we can distinguish between the two gases. They start off with all of being on the right-hand side of the box, all of the other gases being on the left-hand side of the box. You might imagine that the video started, there was some kind of partition down the middle of the box that was keeping them apart, which has just been removed, and then we allow the particles to sort of jiggle about according to the way that molecules usually jiggle about with their thermal motion, and if we let that run, then we see that gradually what happens mix with, and if you leave it for actually not very long in particular, we'll soon find that basically each type of gas within the box. We've got this on a loop, so it keeps on going back to the original state. That's not to be confused with the two separating themselves out again. Now, the reason for this happening is simply, on one level, to do with probability. Because if you were to count up all of the ways in which that there were of arranging the molecules so that gas number 1 was on this side and gas number 2 was on this side, comes to quite a lot, of course, because there are lots of molecules, but it is a minuscule number of ways compared to what happens if you calculate the number of ways in which they could both be mixed up across the whole of the box, evenly distributed, mixed in thoroughly with one another. So simply, if you let the thing evolve at random, the probability that it'll end up coming back to the two being separated again was not zero, but it's so close to being zero, wait for the time in the life of the universe for it actually to arise, or to be even likely to arise with any probability. And where this relates to entropy, this idea of information, is that when we've got the two gases separate from one another, that's really easy to describe. I don't need to give you very much information to say that that's what's the case. I simply need to say all of the molecules of this kind are on this side, and all of the molecules of that kind are on the other side. Whereas when they're mixed up, I have to distinguish which molecule is which in order to be able to tell you what the state of all of this kind when there isn't a sort of rule that I use that applies to all of the molecules of that kind. So what we can see is happening is that naturally, simply by simple rules of probability, this system is evolving from entropy, where not very much information to describe it, going into a state of higher entropy. So, now, the thing that this seems, though, to suggest to us is that the world that we see around us is incredibly unlikely. All of these patterns that we've described, the beautiful plant forms that can be modelled so well by these fractals, the sort of lifelike patterns that we saw emerging in Conway's Game of Life, those sorts of things that we see, the patterns that we identify around us, are areas where entropy is low. That's supposed to be the kind of thing that doesn't happen spontaneously, the sort of thing that is unlikely to arise naturally simply if you let the universe get on with its own merry way. The reason that I'm just going to leave the screen blank lest you become hypnotised by the particles moving around in the box. The reason that that we seem to have this, if you like, exception, or these many exceptions to thermodynamics, is that we don't live in a world which is a simple closed system. That law of thermodynamics only works if you take into account everything that there is in the system as a whole. We know, however, for example, if we think about the Earth as the main source of our examples of lifelike patterns, is a hint of constant radiation from the sun. It's constantly emitting a different kind of radiation out into the universe in turn. That exchange of energy is enough to power the formation of local areas in which entropy decreases rather than increases. So we find structure emerging rather than just disintegrating. And the study of systems where that happens has been one of the most active areas of research across all sorts of scientific disciplines over the last 50 years or so. So the next slide is going to show a different pattern. This is one that comes not from the worlds of biology, mathematics. This comes from chemistry. this is an example of a simulation of a reaction, which I have to look at to pronounce the names correctly, the Belousov-Zhabotinsky reaction. So in this reaction you have different reactions with different colours, and those colours are evident in an oscillating pattern if you allow the reaction to take place in a kind of thin layer. And this is an extraordinary thing because chemists didn't realise that this was something possible until quite late on certainly in the second half of the 20th century. And it's even more fascinating because the first person to predict the existence of a chemical reaction that would produce patterns like this, spreading out in space and oscillating in this way, it was Alan Turing, the celebrated computer scientist and originally all of modern computer science and the theoretical background to it, as well as, of course, the great code breaker of Bletchley Park, and he's rightly celebrated for his many, many contributions to that and all sorts of areas of mathematics. But the thing that Turing is perhaps less well known for is that he wrote a paper where he worked out whether or not it was possible for lifelike structures to emerge out of very simple mathematical models that might plausibly appear in a chemical reaction which didn't have too many different ingredients, if you like. And he came up with a possible model. The model he produced was a mathematical model. It took a little longer for an actual chemical reaction to be discovered that exhibited that kind of behaviour. But it produced sort of irregular patches, and he imagined that they might be, for example, how animal markings might arise, or how the structures from very homogeneous to an embryonic could result in the intricate structure making up a human or other animal body. And the key thing about this phenomenon, and many others like it, that show this sort of pattern emerging spontaneously, and this is a reaction where there's an example of a low entropy state, a very highly patterned state being preserved artificially, that seems to contradict this second law of thermodynamics idea that patterns should sort of disintegrate. The thing or the sort of features that these systems have in common is that they exchange lots of either energy or matter with their surroundings, that they involve lots of components which interact strongly with one another, and that they therefore are very far away, on the one hand, from being sort of closed systems that don't communicate, if you like, with the world around them. But secondly, also, they are very far away from being in equilibrium. And if I just go back, as I said before, I will turn off the video so that it's not too hypnotic. One of the things you see is that the fluctuations just don't stop. They if you like, the feedback and keep themselves going. And these sorts of phenomena, these sorts of pattern creation in our natural world have been, as I say, extensively studied over the last 50 years, when their sort of existence first started really to be systematically studied. And they now come under the heading of what are called emergent phenomena, because what we see happening in these sorts of circumstances are patterns emerging where we perhaps feel we would have no right to see patterns spontaneously appearing. Now, one of the great principles that has helped us to understand, because we could say this is sort of an accident of physics, as it were, that there's no deep mathematics really that underlies what's going on here, that We've understood perhaps the conception of entropy increasing because they exchange matter or energy with their surroundings. We can understand that. Is something which is really quite. If you take certain numbers that you can calculate from things like ratios of the different sizes of fluctuations that appear in them, if you look at them on different scales, you sort of increase their scale, zoom in or zoom out, you see behaviour that behaves surprisingly similarly on those different scales. All of those things exhibit kind of behaviour which is, in some sense, universal. So that you have a wide class of different phenomena where you will look at that ratio between what happens. You'll find exactly the same number, despite the fact that one's in biology, one's in chemistry. And so people began to think there must be some mathematics behind this. And indeed they were right. And the mathematical principle which underlies a lot of these phenomena comes under the rather intimidating sounding title of renormalization. Now, I mentioned about lots of these phenomena having similarities on different scales. The idea behind renormalization was that people looked at these things and said, well, if we're zooming in or zooming out, maybe we should just kind of keep doing that if we expect to see the same thing happening over and over again, no matter whether we look at it on sort of millimetre scale, micrometre scale, or centimetre scale. And what we can then do is see whether a system that obeys some relatively simple rules changes if we zoom in or zoom out. And of course, naturally, for most systems it will do. In order to, perhaps what we might be talking about, here's another little video. This is a fractal curve that we're zooming out from, and what you will observe is that as we zoom out, what we end up seeing is simply a smaller copy of the original that we started with. Now, the idea of renormalization is to apply that to something that perhaps looks a lot less regular than this in the first instance. The surprising thing that mathematicians found, and Robin Wilson was the first mathematician really to take this theory to its to a conclusion where you could really predict this sort of thing happening. You zoom out, and eventually you find that you land on something like this, which doesn't change when you zoom out. In other words, for a large number of different sort of rules, if you like, for how a mathematical system or a biological system or a physical system might evolve over time, if you keep kind of zooming out, eventually they'll all tend to one fixed system that observes that obeys the same kind of laws, has the same behaviour, no matter what you started with. That was a huge surprise to people, that suddenly you've got the solution of a mathematical equation which is completely abstract, has no roots, if you like, in anything specific about any of the sorts of phenomena or systems that were being described, but which nevertheless predict precisely the numbers that you can measure that are the same across all those systems. So what we have is the abstract world of mathematics saying to us, look here, if you want to describe the real world, you may think that if you tweak the laws of nature like this, you can get a different answer to this question. It has to be this way. It is something that is just encoded in the fact that mathematics describes the universe. And so this, I said at the beginning of the talk, we getting to, saying that if we want to look at where patterns come from in the universe, then at least some of that needs to be thought about in terms of the sort of come from a very abstract world of mathematics, not just because we write down some physical laws that we observe and then work out what we deduce from them. Now, I'm going to give one sort of final example of this, just to illustrate sort of how this renormalization phenomenon works. A formula that has become very popular with recreational mathematicians who want to do a bit of kind of experimenting and programming and drawing their own fractals and things themselves. It's a model for how a population of a species might grow over time, or change over time, I should say. And X is, if you like, a measure of the population at a particular time. X subscript n is the population at generation n. So X subscript n plus 1, that you can see at the top, is the n plus 1th generation. And the population, we sort of scale down so that it's between 0 and 1, where 0 is no population, and 1 is the theoretical maximum population that could be accommodated in our environment. And the idea is that to get the next generation's population, you take some number r, which is the sort of reproduction rate, you multiply it by the last generation's population, because obviously if your population is bigger, it's going to be bigger in the next generation. But then you multiply it by, it's a very crude model, but it exhibits some interesting behaviour that's worth noting. So you multiply it then also by the factor that is supposed to represent the competition that there is in the environment. So the closer the population gets to that factor of 1 minus xn gets closer and closer to 0. So if you're very, very overpopulated, then that population is your generation. And it turns out that the behaviour of this model of population depends really sensitively on this number r, the reproduction rate. And you can see on the left-hand side a graph which will show you, for a given value of r, what you end up with in the long term. On the right-hand side, you can see just the calculation of the population from year to year as it is, as the value of R changes. So the videos show us an animation of what happens as R changes from just above 2 to 4. So to start with, I can pause it, that's marvellous. So to start with, what happens is, as R is relatively small, the population jiggles about to start with, but then it settles down to a nice steady state. Now, something surprising happens. As R increases over the value, instead of settling down to a steady number of individuals in the population, it starts to oscillate. Every other year, the population is larger or smaller. Let's see what happens if we allow R to increase a bit further. Right, if you let it get a little bit larger, then eventually you'll find that what happens in the long term is the population will jiggle about between 4 different values. Now let's let it go even further. Right. So, what this graphic is not fine enough resolution to show is that splitting into a population that varies, alternating between 4 different values over a 4-year period, is it then goes to an 8-year period and then a 16-year. But they come and change even so closer and closer together as R increases, in such a way that they build up to a point where beyond that, what happens is complete. And I'm going to so already where we stopped previously looked pretty random, but you can see that's jigging about like nobody's business. But I think I'll see if I can catch it this time if I'm quick enough with the pause button. So it looks, so you have the first doubling right now. Oh, it's too quick then. I'll give it one more go. No, I didn't quite get it. But if you were looking carefully, you might have seen that with a little area. Is this a point? It does. There we go. Just here, where the pattern thins out. And if you caught it as it went past, you'll see actually what happens is that the population varies over a 3-year cycle and repeats itself in that little window. So this is a model of population which has been studied in a huge amount of detail and is theoretically extremely well understood. And the idea of renormalization has been applied to study the transition from order into chaos in this model. One of the things that we see is that if you measure the amount of space, if you like, there is between each of those areas where the cycle doubles in its length, and take the ratio of those, so the sort of how, by what factor of time, by what factor each one gets shorter as you go further and further down this doubling phenomenon, then that tends to some fixed number. It's called the Feigenbaum constant, named after mathematician Richard Feigenbaum, who first discovered this behaviour happening. That in itself is not too surprising a thing. What is really surprising is that if I change that formula completely, it looks sort of roughly the same. It's if you plot that the graph of what that looks like, it's a graph that looks roughly like this. If I were to replace that with a formula that involved some complicated functions and cosines and things, we'll only have one sort of maximum point like that, get exactly the same number appearing out of that calculation. And the zooming in and out procedure that I described as being renormalization corresponds to what happens if you super speed up time, you skip generations each time. And that's how you can prove that all of these different models give the same answer to that what might seem like quite an abstract question, but actually has some real world interpretations. And the reason I sort of give this example, firstly, it's very famous and deserves to be shown simply for another example of how patterns can arise, complex patterns out of simple-looking formulae. But it is a really good illustration of how the structure, the place where that pattern really emerges, is on the boundary between a very ordered world, where everything works on a nice sort of period, where it varies over some regular number of years, and chaos, where there's no sense of predictability at all. And it's that boundary between order and chaos which is where the mathematics of these systems always pushes us. And it's where we find structures which, like the fern here, are similar to themselves under different transformations, magnifications, and so on, but which are not trivial. And for a long time, mathematicians thought that if you had a structure that had different scales, it probably would be rather boring and didn't have any kind of interesting structure at all. And it took the sort of fractal revolution of the 20th century, these discoveries by people like Benoit Mandelbrot and various others, to uncover examples which we now know are actually not the exception at all, but really the rule. And the processes in nature which drive us towards this boundary between order and chaos, where these intricate patterns are to be found, come from this description that we have of how much information something contains. This idea of entropy to suggest whether something is a pattern or simply something that's random. And in particular, the places where these patterns emerge are where entropy is being moved around a lot, where things are being sort of shifted, but where, if you like, we are interacting with a world which we have to remember, the second law of thermodynamics, is all about being subject to decay and patterns disintegrating if you take into account the larger structural picture. So what we have is a picture of the universe in which there are many patterns that arise spontaneously in nature, and increasingly we see that those patterns come because the laws that underlie them are written simply in the language of mathematics. It doesn't matter precisely what laws are, we can tweak them, but the patterns, their general form, will remain the same. And what's more, the processes that drive us to patterns are patterns that are intimately connected with the idea of change, but also the inevitability of decay, but life coming out of a pattern and the law of the universe that does seem to be a destructive force if you look at it in a kind of naive way. Which is, of course, a very it's a potent idea from the point of view of Christian theology, particularly we're meeting very soon after the Feast of Easter, and the idea of life emerging from what looks like death is something that is a very powerful thing for us to see reflected in the natural world. So that sort of draws to something of a conclusion, the ideas I wanted to share with you this evening. But I'm going to finish with a sort of theological note to conclude what we're talking about. As I mentioned at the beginning, and have come back to a number of times, this idea that we should be thinking about the structure of mathematics as being something which is inhabited by God, as well as the particular form that our creation takes. We've talked about things as being logical necessities. Now that word logical comes from a Greek word, logos. And logos is a word which is no stranger to the theological tradition as well. Because if we look into the Greek original of the beginning of St. John's Gospel, we find this. I've not translated the word logos out of its original Greek. In the beginning was the logos, and the logos was with God, and the logos was God. Now, if you pick up your Bible, you will often find that translated as word, and that is the sort of root meaning of the Greek word logos. But actually, already in that time, it meant more than that. It was a word that meant it's rationality, if you like, underlying all of our thought and reasoning and rationality. So we see, actually, deep in the Christian tradition, an affirmation, even in its very earliest decades, that God indeed, not simply in the particularity of the creation around us, but even there, present in the very language in which it's written, the language which we use so fruitfully to describe the beauty of the world around us. Thank you very much. I don't know the form at this stage. They're very happy to answer or attempt to answer only if it is.
Well, if you're happy to take any questions, if anybody has anything they wanted to raise or ask.
Back to one of the slides. It was pointed with a rule that a square. Could you please show it? Yeah.
So the simulation or the
theory behind this is
yes.
comes from this, yeah?
Yes, that's right.
And it's like a program by someone to repeat it.
Okay, yes. It's the first example of what's called a cellular automaton. So after John Conway came up with this idea and found that it exhibited some exciting behaviour, immediately lots of other people started. And you can do all sorts of interesting generalisations. You don't have to do it on a square grid. It could be a triangular grid. You can do it in multiple dimensions. And you can vary what the rule is. And different rules produce different kinds of interesting phenomena.
So on the next slide,
yes,
please. Yeah, it begins with 8.
yes,
And it's been written to repeat the same rule
yes.
till you said 50,000, 5,000 something.
It was between 5,000 and 6,000 iterations that we got to by the end of the slide.
Continues and continues.
So yes, if we, I won't be able to jump to the end of the video. I think he's in control here. But in the final state that was arrived at, we had a collection of little units that were stable, so that the rule would not change them. They had, if you apply the rule to all of the squares in those little blocks, they would simply stay the same because they had. Suited to being stable under that particular rule. You would have a few more configurations that were a little bit wider that would oscillate between two different states. And then you would have some collection of these so-called gliders that would just carry on moving in the same diagonal direction to infinity. Yes.
I just wanted to now be triggered by that program.
Yes,
their
that program is the only ingredient, if you like, other than the starting position, to arrive at all the rest of the video that we saw. We can let it play. It was rather entertaining to watch. I was showing it to my children earlier, and they got very excited whenever they spotted one of the gliders. It's getting away! It's getting away!
Does that apply to evolution?
Well, now this is an interesting one, of course, because there's no reason why it shouldn't. Evolution is a system that we can model using kind of mathematical models. It's very complicated, of course, to model, but one of the things that we have seen is that, if you like, fine details of the model, they might affect some aspects of what you can predict, but there are other aspects that are, if you like, completely independent of it. And one of the features that evolution has in these things is it these so-called disciplines where there's lots of matter and energy being exchanged. And indeed, if we think about natural selection, what is the engine that kind of keeps natural selection working? It's mortality. So that's entropy yet again showing that in order to have this evolution of structure, these new structures appear as life carries on, somehow we need to have a mechanism by which things die in order to allow that to happen. Because if we don't have any entropy, any of this information being exchanged with the environment, then we can't have the patterns either. Actually, a very timely thing, because the view of evolution as this kind of process and driven towards endpoints which are particularly patterned is one that is associated with the role of the with the work of the one of the most prominent scholars in evolutionary theory of the moment, and so Professor Simon Conway Morris, again the Cambridge connection, who actually just, it was announced I think yesterday, was this year's recipient of the Templeton Prize, which is the foremost prize for scholars or thinkers working in the area of science and theology. So yes, absolutely. I think evolution is definitely a really strong candidate for more of these kind of explorations to be done on it. This is the thing, of course, and that's largely how it's presented in the popular scientific literature. You can pick up any number of books off the popular science shelves in a bookshop that will tell you that the main lesson you have to learn about entropy is that it implies the heat death of the universe, whereas actually the movement of entropy is responsible for all of the beauty, glory, the structure and pattern. The fact that it is also intimately connected with death and decay, as I say, perhaps has something to teach by way of a theological insight into how we think about the world around us.
Excellent. Well, remains to Alex for coming to share some interesting insights, not about being able to look at the world around us, but being able to, as you say, apply those much deeper understandings as to what might be on. And as we look at a world that seems to be tending towards chaos, perhaps there is hope for some structure and some stability to emerge from it. And so, thank you very much for being part of the Haverhill Science Festival and for sharing your thoughts with us. Please do say, if you've got other questions, I'm sure Alex wouldn't mind just staying for a few moments longer afterwards and answering any other questions. Please do look out for more of what's going on, so do be involved in those. Thank you again to Colin for being here to represent One Haverhill Partnership and the Town Council.